vehicle collision system. And the reason we show this project is because vehicle collisions is a problem that we have in the United States. And if you look at statistics from 2009 to 2010, the numbers of vehicle deaths has fallen, but the number of injuries has risen from 4.1 million to 4.4 million. And the reason for that is because people have distractions while driving. They have distractions texting, eating, taking their eyes to look at something, and that's why we chose this project. And if someone takes the phone to text, it takes 4.6 seconds to actually write a text on a phone. And if you're traveling at 55 miles per hour, that's similar to traveling a whole football field blindfold. So we designed the project using infrared technology, ultrasonic technology, using the Bobot. And we have Mrs. Mentong is going to talk about the hardware that we used.
Now I will talk about the hardwares which we have used in our project. This is the board of education, and you can see the key specifications beside it. And I will talk about the details about this board. The number one is 9 voltage battery clip, and the number two is barrier jack. They are intentionally positioned, so we cannot use both at once. And number six is power header. It includes VDD, VIN, and VSS. VDD connects to plus 5 volts DC, and VIN connects directly to the power. VSS connects to the ground. And the number 7 is the breadboard. We can use this breadboard to connect all components to each other and build circuits. The number 8 is the I/O pin access header. It has 16 pins, and they are connected to the basic stems. The number and it is also brought to the number 5 and the number 9 headers. The number 5 is server headers, and the number 9 is app mode headers. And the number 12 is a scout for the basic stems. And the next I will talk about our basic stems. We choose the basic stems too because of plentiful sources are available online or in print, and I'm sorry. And it connects to the power indicator LED, the program connector, and all I/O pin headers. And next, I will talk about the servo. We use 2 servos. On the left, this is continuous rotation servos. We use 2 of these to make our car drive, because it can drive rotation. We use one of the standard servo in front of our car to make our ultrasonic sensor turn left or turn right, because the standard servo can only rotate 180 degrees. Then I will talk about the ultrasonic sensor. The ultrasonic sensor can measure the distance on an object. There are two different ultrasonic sensors, and we choose the left one because it has 4 pins, and it is easier than the right ultrasonic sensor to program, and the range of the left ultrasonic sensor is bigger than the right sensor. They are all we used in our project. Next, my team member Luan will talk about the software class.
And let's talk about the flowchart and the program. I will talk the flowchart first. This is when our car is running, then the ultrasound sensor is also working. It detects the object in front of our car. First, if there is block objects in front of our car, then it will judge. If the object in the safety distance, then it will check the left part. If there is also a also object in the left safety distance, then it will check the right.
What do you mean by center block, left block, right block? What do you mean by
the center block is in the object in front of our car in the safety distance. If there are objects around the screen
there is an object in the center.
That's what she means.
Yeah.
Yes.
That's what she means. If the object is in one
Center is blocked.
Yes.
And left is blocked and right is
But then
blocked.
she's saying, Jen, she says, yeah, so you mean is the center blocked in a safe distance so that you can go on and now look to the left or the right? Because you're saying, yes, there is a block,
Yes.
and you're going now to look at the left? I mean,
Yeah.
It's going to look left.
Then
and
check
it's
the
gonna look
right side.
so in other words, you don't want to stop
Don't you have to stop?
because you're going to hit it.
No, if there
No, you
are
wanna make
three
it turn.
blocks, three sides, there are objects, then the car will go backward, then continue to go forward.
So if there's an object in the center, then it looks to see if there's an object on the
Right,
left.
that's
If there is none, then it goes left.
Yes.
And if there is,
So do you
but
have
if there is something there, then it checks to see if there's something on anything on the right.
Can you check center, left, right at the same
No,
time?
you can't. You got to
No,
stop.
no.
You have to stop.
You have to stop.
Yes.
Right. Yeah.
This is the outline flow chart, and then we will go to the software, the main code. We use P basic language to write our code to programming. And in P basic language, this is when a programming starting, and the programmer defines definition the version of basic step. This is the basic step, and the version of the P basic will be used, and the constants and the values are usually defined in the first of the programming. And this is the safety distance of our car. We calculate based on the frequency and the pulse of our servo, and this means pulse 5 microseconds pin 1, and this is pulse in the time the ultrasonic detects for 1 microsecond, millisecond to pin 15. And this is the code for our car go forward. It took 41 milliseconds to pull out. This is the code for when the car, before the car running. It check the ultrasonic, make the ultrasonic sensor is go right ahead of the car. This is degree of the right ahead, and after 20 milliseconds, then the car will start. And this is the value for the car. When we pause out 852 pin 30 and 615 into P12, then make the car forward, and the same then. This is the turn left, right turn backward. This is our main code. This is our main code of ours.
What does P13 and P12 mean?
It's the pin. It controls the where servo of the wheel.
Why do you have two different values and when you have a going forward?
This is a pulse. Yeah. Different pulse to the different servo, then make it turn left and turn right.
Is that the number of pulses?
Oh, sorry.
What is 850? 850 is the number of the pulses per second?
Yeah.
Or something?
Million second. Yes.
Per millisecond?
Yes.
850 pulses per millisecond or 800?
Not that big.
This number means the pulses is sent to the pin. It sends to the pin. That means the pin connects to the servo. It means that this 850 means the pulses are sent to the servo. But because we use this servo, it's not a motor. It's not a motor. It can to make the servo work. We must keep sending pulses into the servo. We can just if we just roll this, the servo will move and stop because there's no continuous pulsing into it. We must define another time period. During this time period, it will send 850 times pulses to the servo.
No, my question is, your number doesn't make sense to me because the left one you put
because
850, the right one is 650, you go forward. And then you have 850 on the left, 750 on the right.
Yeah.
It takes right turn.
Because when when the number was set at 750, the servo will stop, will not move, no matter how we define the time period, no matter what. Because it's like a clock.
This is
The center horn
between
is
two.
positioning right to the 12 o'clock, so it doesn't move.
750. Like
You gotta tell them we have two wheels on it.
Yeah, we only have two wheels. So because it was reflected, so we must make one move forward and make another one to this one is moving backward. But when it changes to another side, it moves forward.
That's because there's two wheels on it.
Yeah, that's our main code, and she will talk about our budget and our timeline.
Firstly, I will introduce our website. The website is the platform to show our achievements and ideas. We update our website every week to upload our weekly report and particularly victory and our problem we faced. Some of the videos and our hardware we used and the weekly report. Next I will introduce. Next, I will introduce our work procedures. We have worked on this project for 1 year. Last semester, we focused on confirming the project and her ideas, and we did some research for this project. This semester, we worked on searching the hardware first, and we ensured what we needed and buy the hardware from the website. And the most challenge we faced is our software, because this is the first time we used the T-basic language. It cost us a lot of time to testing the program. Although we make a lot of mistakes, but we completed our project successfully. Next, I will introduce the budget. The board of education is cost us $96.99, and the basic stamps too cost us $49, and the two server, the rotation server and the standard server are the same price of $12.99. The ultrasonic sensor, which was there's HCSR, therefore is $80.4. Next, my teammates Bob will do some demos.
I think most professors have some pop questions about our course. Next, I'll go into the very details of it. First, we define several pins, and maybe these words we can use variable in my program. And next, I remember at first Professor Saito asked when it does the check left and right, will it stop? And because this is the main loop of our program, and we make every, like get distance or check left or turn left or center block or left block or all block. Everything we make it a subroutine, and every time it goes out of the main loop, it goes like doing the left block. Going to the left block, the subroutine will stop. We'll pause. We'll pause for a sec for the left block to finish, and when it goes return to the main loop, and it will do some options, and then it can continuous forward or turn left or check right, and the same as we introduced check right. And these numbers, because 750 is it's the horn directly points to 12 o'clock on the servo. The servo is like a clock face. There's a cross on the right in front of the servo, and one horn one foot is regarded as a horn, and every time it was set to 750, it means that the horn goes back to 12 o'clock. Goes to its initial position. doing the blocks, left block, and in the left block, it first, cause the main loop goes to the left block. It means the left was detected obstacles, and it will firstly go check right. This capital turn right, it means make the servo of the ultrasonic sensor turns right. Check right and then goes up, get distance to make ultrasonic sensor work. We set the safe distance in 15 centimeters. And if it's blocked, it will go sub all blocked, and else it will go to the subroutine of turn right. And let's see the turn left and turn right. Turn right is here. I set this number. I set number to this for counter equals 1 to 60. It means during this time period. The 60 doesn't mean 60 nanoseconds or millisecond. It means I used the time to divide it by the frequency reads the servo itself and equals this number. Because the two servos are different because these numbers are different. These two numbers are not the same, and this number is means make the pin 12 wheel stop and only make the pin 13 wheel move, and so it can make turns. And this means every time after its every option, make the servo turn directly forward of the car. Because if the servo doesn't move when the car turns left, the servo will still keep looking the car's left. It means it's not the right direction. So every time it turns, I make the servo to turn back to the car's front.
You don't have to explain everything. If you have demo, I think we're running out of time.
Okay. Oh, sorry. Yeah. See. Firstly, see the videos. We run it in our dorm. And next it goes into my room. Because I put my camera in front of the car. And this car is left priority. If it detects left, there's no obstacle on the left of the car, it will turn left without checking the right. Now that's after release the reset button. After release the reset button, it will go straight forward. It's not. It's very loose. The line to connect is very loose, so it's not very stable. And balance, cause I took the battery out of this battery packet, so it's the front of the car is too heavy. Every time you're doing a very fast move, it will lose balance. But it's very. What?
For the low wheel.
Yeah. At first I want to put this, but my team leader asked it's better to take the battery out, so not to waste the battery.
Wait.
Just to put the weight, some kind of weight.
The counter.
Yeah. Oh. This is only the only problem is that it's the wire here maybe it's too old or something is loose somewhere. But every time it detects the obstacle, you will see it can turn left or turn right or go backward as we thought. And next, my team leader will do the conclusion of our project.
Thank you very much. I hope you enjoy the show. And not only can you use this on vehicles, but you can use it on boats. Say, for instance, we had a cruise line that went into some rocks, and if it had some sensors to avoid that because the driver was drunk or impaired, it had avoided that. Or it could be used, same thing, another boat that we had a few years ago here, that goes to New Jersey. They crashed and hurt and injured some people. Or even better, you can use this to go reverse or forward in a garage. Instead of using the tennis ball, the car automatically stops at a distance that detects and won't crash into the house.
In your report, you said something about first thing you do temperature sensing. Did you implement
Well,
this
that's
or?
the temperature is. If you were to apply this to a real application in the world, you have to take a temperature into consideration because the ultrasonic uses echoes. It depends on the temperature to distinguish how fast the signal goes out and back in.
So it's part of the algorithm.
Well, the temperature, yeah. If depending on the temperature, it's a delay.
Say, your introduction and your conclusion was about collision avoidance system. Okay, but the content is basically nothing much to do with the collision avoidance system.
But it's a prototype, so what you can use that is for, say if you're driving on a one-way street and you have a person crossing the street and a car. Of course, different manufacturers have different weight, so the brakes have to be applied at a specified distance to compensate weight, and that's to avoid a collision in that manner. Or it can be used if you're traveling at the highway and you're trying to make a right turn, or the next person is trying to make a left, if you have sensors on the side.
If on the highway, your car don't automatically turn left or right, okay? Your driver.
Yeah. But that's now. But just recently, a car was able to drive by itself with a person blindfolded. So I believe that the industry is heading that way.
In Appendix B, you put a control system block diagram there, but without any explanation, without any calculation to explain what you wanted to do over there. Can you explain?
Which one?
You have a general control system. You show an R,
Yeah,
E.
you
You
show
don't
the control
say what
system.
those
How did
variables
you
are.
implement in your design?
Well, at the moment, I don't have that on it, but I can read. You want to what?
this.
Explain this. You put control system principles block diagram over here. So what do you want it to accomplish? What do you want it to show over here? Then what have you implemented in your design?
So if you put an object in front of the device, it's able to stop or make a decision based on what's in front of it.
So explain to me here. You have an arrow. What is the arrow? What is R? What is Y? What is YM? What is U in your system?
I can really can't do right now.
What's that?
Yeah. No, I have to get back to you on that.
You don't know why you put it here.
It's just a generic control system.
Then you
Yeah, of course.
explain.
You have any questions?
You understand the question? You included this,
I did.
then you have to, we don't know the relationship between this one and the actual design.
Yeah, I'll take it back to you.
Did you include any of this in your design?
I did, but I didn't update
You did.
scientific compound.
That's why I came back. Thank you very much, appreciate it.
All right, thank you.